History.
All right, this is part B1. First one, approximate length of an unsharpened number 2 pencil. Here is a number 2 pencil. It's sharpened a bit, so yours would be, if it was unsharpened, to be a bit longer. And our choices, now these approximation problems are usually just a question of, do you understand what scientific notation is and just the approximate reasonable sizes of things. All of these are 2. 2.0 times 10 to the minus 2 meters times 10 to the minus 1 meter times 10 to the 0 meter and times 10 to the 1 meter. So we're here. I have a ruler. You're going to have a ruler like that. So we're looking at 2.0 on the ruler, maybe 20. So this thing is 20 somethings. I look at it and I see it's 20 centimeters. Now on the rulers, a lot of times they'll say mm. The millimeters are the little ones. Hopefully you've figured that out by now. The numbers are actually centimeters. The little tick marks are millimeters. So that's 20 centimeters when you read there. So we just let's take a look at what centi is. Centi is 10 to the minus 2 meters. All right, 10 to the minus 2 meters. And if we wanted to make this 2.0, I moved the decimal point one place here. I made this smaller. I have to make this bigger. So this is going to be -1, because 10 to the -1 is 10 times bigger than 10 times 10 to the -2. So I made this one smaller by a factor of 10, and I made this larger by a factor of 10, and so this would be the answer. All right, let's remind ourselves why 10 to the 0 is 1. Well, we know that 10 to the 2 is 100, so it just stands to reason 10 to the 1 is 10, and therefore this must be 1. If we look at the trend, this is 0.1 and this is 0.01. So we see the trend, and in that case it makes sense that 10 to the 0 is indeed 1. Number 37, conservation of momentum. Let's draw a picture. The things, of course, that are conserved, the things that are conserved in nature are energy, momentum, charge, and yeah, that's about it. Those are the big ones that we're covering. All right, always draw a picture. So beforehand, we had a velocity and two carts of different masses. And afterwards they collide. And what does it say? After the collision, the 4-kilogram cart moved to the right. All right, so after the collision, the 4-kilogram cart is moving to the right, like that. Let me draw the ground. 4 kilograms, 8 kilograms. 8 kilograms. I'm not going to put the significant figures in there just because there isn't room. All right, conservation of momentum. Write down the equation. First thing, to get full credit. P before equals P after. In a closed isolated system, momentum is conserved. So anyways, we had 4 meters per second, 6 meters per second, and here we had 3 meters per second. All right, so we have, we're going to have momentum before is the momentum of this thing plus the momentum of that thing. Keep in mind, we're going to say the right is positive and the left is negative. 8 kilograms times 4 meters per second, and that's positive because it's that way, plus 4 kilograms negative 6 meters per second, and that's where you might run into some problems ignoring direction. That equals what happens afterwards, which is 8 kilograms times the velocity of the, I'll put velocity 8 of the 8 kilogram, plus 4 kilograms, the momentum of that, times 3 meters per second, and that is positive. And solving for V8, we get the velocity of 8 is going to be 8 kilogram meters per second minus 12 kilogram meters per second, all divided by 8, which is negative 0.5 meters per second. So we ended up with negative 8.5 meters per second. So that's that way. And 0.5 meters per second. Does that make sense? Looks like they bounced off each other. Sure, why not? All right. And the negative, actually, we shouldn't. We should actually just say 0.5 meters per second that way. What's the choice? 0.5 meters per second to the left. That would be choice 1. This is problem number 38. As a result of these forces, what's the block going to do? Well, let's add them up. If it's in equilibrium, it's going to be at rest or constant velocity. If there's an unbalanced force, it will accelerate in the direction of the unbalanced force. So let's add this 2 ways. Let's take a look at it like this. I have 100 going this way, and I have 120 newtons going that way, and I have 80 newtons upward and 80 newtons downward. All right, so just kind of a shortcut to adding these, we could clearly see that these two don't supply any unbalanced force. And when we add these up, we're going to lose the 100 and we're going to lose that. So we're actually going to end up with just 20 newtons going this way. We can see that we're just going to have an unbalanced force of 20 newtons that way. We just see that that's 20 bigger that way, and that's what it adds up to be. And that's a nice, quick, and convenient way. We could always add these up in the normal vector addition mode. We could say, okay, well, I have 80 newtons here, so we're just going to add these up tip to tail. I do 80 newtons, then we go over 100 newtons, and then we go up 80 newtons, and then we go over 120 newtons. Let me put this 80 here. All right, so our resultant is from where we started to where we ended, and we started here and we ended there. This is indeed 20 newtons of that way. So it gives us the same answer regardless of how we do it. All right, so we have 20 newtons that way. That is our net force. Let's recall, acceleration is caused by a net force. And the acceleration will be in the direction of the net force. And this will accelerate to the left. Number 4, moves at constant speed to the right. No, it's definitely not constant speed. It could be moving to the right. Moves at constant speed to the left. No, it's not constant speed, it's accelerating. It could be moving to the left. Accelerates to the right? No, it accelerates to the left. All right? So this could be moving this way, we could have a velocity this way, in which case, if it was doing that, it would be slowing down, right? It could be moving this way and slowing down. Or it could be going this way and speeding up. All right. Number 39. If a motor lifts a 400 kilogram mass a vertical distance of 10 meters in 8 seconds, the minimum power generated by the motor. All right, so we have to calculate how much power it's going to take to lift something. So power is the rate at which energy is used or supplied or something like that. It's energy divided by time. And I think the easiest way to look at this one would be what happened. So what's the work that needs to be done to this 400 Newton block? It's going to lift it. No, 400 kilograms, sorry. 400 kilogram block. It's going to be lifted 10 meters, right? It's going to start here, and it's going to be lifted 10 meters. All right. What happens to the work done? The important idea with work is that work changes the energy of the system. So the work you do in lifting that will become gravitational potential energy. And we can calculate what that is. So really, this is going to be the gravitational potential energy divided by how long it takes. But that's just going to be mgh divided by t. And it's actually the change in gravitational potential energy. What do we have? 400 kilograms times 9.81 meters per second squared times the height, which is 10 meters, divided by the time, which is 8 seconds. And it's 4,905. This would be joules per second or watts. Watts. Watts are probably a better unit. Which one is that? It's going to be two significant figures. So it looks like 4.9 times 10 to the 3 watts. Choice 3. Number 40, a 4 kilogram object is accelerated at 3 meters per second squared north by an unbalanced force. The same unbalanced force acting on a 2 kilogram object will accelerate this object north at what? All right. So let's see. So here's our 4 kilogram object. And it's accelerated 3 meters per second squared north. Let's say this way is north. So north is this way. That way is north. And has an acceleration of 3 meters per second squared by some force. All right. And so the acceleration is going to be 3 meters per second squared that way. Also, acceleration's in the direction of the net force. The same unbalanced force, all right, it's unbalanced, there we go, is acting on a 2 kilogram object. 2 kilograms. Maybe I'll make it smaller. Made out of the same stuff, so it would have half the volume. 2 kilograms. Same unbalanced force, F. What is the acceleration? All right. Well, acceleration, of course, is F net, but this is, I'll call this F net, because they said it was the unbalanced force, divided by m. Well, we could calculate the net force. That would probably be the most straightforward way that many of you would be comfortable with. Or I could say acceleration 1 and acceleration 2. Let's do that. Let's do that. Acceleration equals that. Acceleration 2 equals the same net force divided by m2. All right. And we know m1 and m2. So let's combine these equations. We could just say, okay, m1a1 equals f net. m2a2 equals f net. So they both equal f net, so m1a1 equals m2a2, and therefore a2 equals m1a1 over m2. Am I still on the board or still on the screen? I'm not sure. M1 is 4 kilograms times 3 meters per second squared, all divided by m2, which is 2 kilograms. That's going to be 6 meters per second squared. Does that make sense? I have half the mass. So for the same force, I would expect double the acceleration, because we could see that the acceleration is indeed inversely proportional to the mass. So anyway, 6 meters per second squared, which is 2. Choice 2. 41. An electron is located in an electric field of magnitude 600 newtons per Coulomb. What is the magnitude of the electrostatic force acting on the electron? Oh, all right. So here's an electron, and I'll put it in a uniform electric field. Let's say it's like that. All right. So it's in an electric field. Which way is the force going to be? Well, the force, the electric field is defined as in the direction that a positive test charge would feel a force. So if I put a positive test charge there, it would experience a force this way. All right. So therefore, our electron experiences a force this way, like that. All right. Anyway, so there's our electron in an electric field. And the electric field has a magnitude of 600 newtons per Coulomb, okay? You give me a Coulomb, a charge, you plop it in there, it's going to feel a force of 600 newtons. And if it's positive, it'll feel a force that way. If it's negative, it'll feel a force that way. What is the magnitude of the electrostatic force acting on the electron? Oh, well, of course, we have the hidden information. They said it's the electron, so we have the charge. So the charge is going to be minus 1.6 times 10 to the minus 19 coulombs, or minus 1e. Which one of these should we use? Should we use coulombs or elementary charges? Which one's the standard unit? That's right. The Coulomb is the standard unit. Very good. Give yourself a gold star for getting that right. Elementary charges are convenient units for certain things, but they are not standard. So anyways, the electric field is the electrostatic force divided by the charge on an object. That's a definition. And actually, the gravitational field is a gravitational force divided by the mass. You can see the relationship. They're very similar between electricity and gravity. Anyways, let's take this one. And let's see, what are we solving for? The electrostatic force is the electric field times the charge is 600 newtons per Coulomb times minus 1.6 times 10 to the minus 19. All right, I once wrote a poem with the word Coulomb in it, and it ended with, get off my futon, Dulomb. All right. It's not easy to rhyme with Coulomb, but I pulled it off, and pulled it off quite spectacularly. My students enjoyed it immensely. Yeah. Why wouldn't they? 9.6 times 10 to the minus 17 newtons. Newtons. 3. That's plug and chug city right there. That's making some of you feel really comfortable. The current in a wire is 4 amperes. I'll write that down. The time required is, okay, so that's what they're asking for, for 2.5 times 10 to the 19 electrons. All right, so that's the charge. Is 2.5 times 10 to the 19 elementary charges, because each electron has an elementary charge, each proton has an elementary charge, each positron has an elementary charge. Oh, well, that's just too easy. That's just the definition of current. The definition of current is the amount of charge that passes a single point in time in a single spot in a point of time, which is 2.5 times 10 to the 19. Oh, that's no good. I got a problem. I'm using elementary charges. I need to convert that to coulombs. Get off my futon, Coulomb. So let's convert that. Let's multiply by ones. I know that one elementary charge is 1.6 times 10 to the minus 19 coulombs. Get off my futon, Coulomb. 4 coulombs. Coulombs. Get off my futon, Coulomb. So anyways, the amount of time is going to be delta Q over I. Shouldn't that be me? Has anyone taken an English test recently? I don't think it should be over I. I think it should be over me. 4.0 coulombs divided by 4. Oh, well, I can do this in my head. 1 ampere. 1 ampere. 1 ampere. 1 second. Coulomb per amp, which is a second. 1 second. Choice 1. 42 is 1. So we have 2 charges. We have Q1 and Q2. And there's a force between them. Let's see what it is. The electrostatic force is K. Q1, Q2 divided by the distance between them squared. The distance between them squared, R. All right. That's the first case. In the second case, we have, what do we have? We have 2 times Q1, 2Q1, and we have 4Q2, so it's bigger charges, and how much are they separated by? 2R. Now this is where you have to be careful. This is where you could really mess things up a little bit. If you just say 2R squared, and then I would go, no. You need to square the whole denominator. So that's going to be, you're going to end up with something like this. 2Q1, 4Q2 over 4R squared. We can get rid of those. This looks like it's just going to be 2 times bigger. 2K, Q1, Q2 over R squared. Something like that. That looks like it's 2 times bigger than that. So this is going to be, if this is F, then this is 2F. Right? That's F right there. It's F. So it's 2F. Right? This is F right here. F. Choice 2. Yeah. The composition of a meson with a charge of minus 1 element charge could be a meson, of course, is a quark and an anti-quark. Quark and an anti. We put a line over the top that's anti. That's what a meson is. It's right in your reference table. Check it out. If you don't believe me, I wouldn't believe me. And it has to have a charge of minus 1e. All right. Well, right off the bat, I can get rid of 2 and 4 because 2 is 3 quarks and 4 is 3 antiquarks. So neither of those are happening. Those aren't mesons. Those are Yeah, those are baryons. Okay, so let's see a strange. Let's see a strange and an anti-charm. So a strange is a charge of minus 1/3 elementary charges, and an anti-charm has a minus 2/3 elementary charges. Since a charm is plus 2/3 and anti-charm, so that equals -1. I'm thinking it's choice 1. I'm thinking that. Let's see what's wrong with choice 2. Choice 3, I mean. And up has a charge of plus 2/3. Well, alrighty, we're heading in the wrong direction. We're positive. I'm positive we're heading in the wrong direction. Anti-bottom. All right, anti-bottom. Plus 1/3. All right, so we're looking way too positive. Way too positive. So that's the answer right there. Which graph represents the relationship between the kinetic energy and the speed of a freely falling object? Find a mathematical relationship between the axes. See if you can find a relationship between speed and kinetic energy. I think you can. I think it's right here. Kinetic energy is 1/2 mv squared. It's the same object, so it's going to have the same mass. Let's see. All right, let's perform extreme physics. We'll graph it. All right, let's see our V in kinetic energy right there. When V is extremely small, with 0, kinetic energy is 0. When V is big, and kinetic energy is really big, so we got 0, 0, big, big. Is that linear? No, of course that's not linear. Our x variable is squared. That is an exponential function, and it kind of does something like that. I guess that's 3. Know your extreme physics. Which diagram represents the electric field between two oppositely charged conducting spheres? All right, we got this charged object, we have this charged object. Conveniently, they've oriented them the same way in all of these. Let me get a positive test charge. Here's my positive test charge. I'm going to do a thought experiment. It's right here. If I put my positive test charge in around this, somehow space has changed. We say there's a field here. I'm going to see which way it experiences a force, because the electric field's defined as the direction of the force. So if I put it here, positive test charge, of course, is going to be repelled. Two positive charges are going to repel and attract it here. So actually, anywhere along here, it's going to experience a force like that, right? Right off the bat, I could see it's going to be number 3. Anyway, so, but let's think about further. If I put it here, it's initially not going to notice that one. It's going to feel force that way. But then, as it gets farther away and a little closer to this one, it's going to notice that one. It's going to curve around like that, and then we go something like that, and so forth. And I don't know. I hate that they draw these without them looping around. Really, what happens is they do stuff like this, like this, like that, like that. All right. So know how to draw your electric fields around point charges. Parallel plates, zoink. They're very important. Also called capacitors. Also called Mr. Hoppers. Mr. Hoppers, the bunny. The bunny with an attitude. Mr. Hoppers. Let's go evenly charged here. The nice thing about parallel plates is the electric field is constant in between them. Let's see, which way is the field? It's going to be repelled from the plus, attracted to the minus. So the field between these parallel plates will look like this. Notice I draw touching each plate, and I draw them evenly spaced. Evenly spaced. Let's make it a little bigger. Evenly spaced. All right. There will be a small fringing about the edges, but that's not the important thing. The important thing is that the electric field is the same everywhere between them. And the force on a charged object is the electric field times the charge. And that tells us that no matter where I put my charge, it's going to feel a constant force because the charge doesn't change, the charged object doesn't change, and it's in a constant electric field. So no matter where I put it here, here, it's going to experience the same force anywhere in this constant field. 47. Which graph represents the relationship between the magnitude of the gravitational field between two masses and the distance r between the centers of masses? I think, yeah, I think I'm so happy that I learned extreme physics at the beginning of the year, because now this is just the gift that keeps on giving. Thank you, me. Thank you for teaching me this. I'm so happy that I did that for myself. Force of gravity, let's get a relationship between two masses. All right, so we have two masses. Here we go. Mass M1, M2. Between their centers, and that's a key idea. Between their centers, the gravitational force is proportional to the product of the masses, inversely proportional to the distance between them. All right, so that's going to be the mathematical relationship right there. Let's make a data table of the force. So when r is 0, but r can't be 0, but it can be extremely small. So when it's really small, Fg is really big. Force of gravity is really big when they're really close together. And when they're far apart, r is big. The force of gravity, of course, is small when they're far apart. All right, and so that's going to look like that. I should have drawn it here. Small, big, small, like that. That's looking like 4. 4. Also, remember while we're here, the relationship, the force of gravity, if we're on the surface of the Earth, if we know the gravitational field strength, the force of gravity is the mass times the gravitational field strength. And always keep that in mind. That's the relationship between weight and mass. Don't confuse weight and mass. It's going to come up many times on the test. You will pay dearly by ignoring them and treating weight and mass as the same. You'll lose points on multiple locations. 48 looks like a wave problem. Diagram shows two waves moving towards each other at equal speed in a uniform medium. They must be equal speed. They're in the same medium. If it's uniform, the medium determines the speed, so it must be equal. All right, when they're in that center section, right there, A and B, when the first one gets there, it's looking kind of like, that's better. All right, so when that one gets there, if you look at it, they're equal distance. The other one is also going to be there. And the principle of superposition says when two waves are in the same place at the same time, they add up algebraically. So this thing is going to be double. I don't know if that's double, but bigger, double. That is, we've constructed something more. That's constructive interference, which is 4. Number 4 conveniently fits right in there. Number 4. Looking like diffraction, the first member of the Coulomb family. Here we have a barrier. And we have some waves impinging on the barrier, going like that. Is that a small opening or is that a large opening? Well, I could fit an entire pen cap and pen through there. Does that make it large? Right? You can't choke on this cap, by the way. It's impossible. Don't even bother trying. This is a small opening because it's small compared to a wavelength. So this is a small opening, and diffraction is the bending of waves around barriers. Now to this wave, this looks like just barrierness. There's barrierness on this side, barrierness on this side, barrier everywhere because it's a small opening. So what's going to happen is, let's see, it's going to be about right there. We're going to get diffraction, lots of diffraction. The wavelength will stay the same as long as, it looks like we're in the same medium. So it's going to, we're going to get something like that on the other side. The wavelength's going to stay the same. So it's looking like choice 1. Wavelength's not going to change. Only time the wavelength would change is if the speed changed. And they don't say the medium's changing, so you can't assume that it is. All right, make sure you know all the different situations with diffraction. That would be a lot of diffraction if we do it like this. So now this is hitting a barrier. This is a large barrier because it's large compared to a wavelength. Wavelength is, so the next wave front's going to hit here. Next wave front's going to be about here. The center portion isn't going to be affected because it doesn't hit anything. And then these are going to bend around like that. So we'll get diffraction around the edges like that. And we get something like that. We say that's less diffraction because much of the wave is not diffracting at all because it's so far from the edges. All right. Also know how to draw it around if you have a glop of something, Know your diffraction patterns. The graph below represents the relationship between energy and equivalent mass from which it can be converted. What is the slope? Oh, man, more graphing. All right, wow. Really, energy equivalent mass, we're going to use E equals mc squared. All right, there it is. C squared is the slope. C squared is the slope. Speed of light squared is the slope. 9 times 10 to the 16th meters squared per second squared. And that's the end of B1. A 25-meter length of platinum wire of cross-sectional area 3.5 times 10 to the minus 6 meters squared has a resistance of 0.757 ohm at 20 degrees C. Calculate the resistivity of the wire. All right, so resistance, of course, is a measurement of how difficult it is to move electrons through, or generally charged, but for circuits it's going to be electrons through a wire or some sort of conductor. Resistivity is a property of a material, like a metal like copper. Now they said 20 degrees C, and the reason they said 20 degrees C is because we have a table of resistivities on your electricity reference table page, and it's platinum wire. Wow, platinum. And the resistivity of platinum at 20 degrees C is not there. All right. So can't use that. Can't use the table. 20 degrees C. They fooled me. They fooled me by saying 20 degrees C, but platinum is not there. There's only one relationship we're going to be using resistivity. The resistance of the wire, of a hunk of wire like that, is what it's made out of, the resistivity, times the length of the wire. There's the length of the wire, times divided by the cross-sectional area. There's the cross-sectional area. And they're going to be round, so we have cross-sections of circles. I'll calculate the resistivity of the wire. They gave us the length is 25 meters. They said that the area is 3.50 times 10 to the minus 6 square meters and has a resistance of 0.757 ohms. Calculate the resistivity of the wire. They didn't have to give us a temperature. I don't know why they did. All right. Well, let's just rearrange this equation. Resistivity equals RA over L. So the resistivity, let's do it over here. So the resistivity equals 0.757 ohms times the area, 3.50 times 10 to the minus 6 meters squared, divided by the L, 25. There we go. 1.06 times 10 to the minus 7 ohm meters. And that seems reasonable, because if I look at my table, they're all like 10 to the minus 8. This is 10 to the minus 7. It's in the ballpark. I'm going to go with that answer. Hopefully it's right. I don't know. Draw at least one full wave, the same amplitude. Same amplitude, so we're going to want it to go one from here to here. And half the wavelength. All right, so our wavelength here is from here to here. So our wavelength is 4. So our wavelength, and this one's going to be 2. If we start it and draw it like a cosine wave, we're going to start up here. Halfway between, we're going to be down here. So we're going to kind of go like that, and there we go. At least one full wave, so I've drawn one full wave. If I wanted to keep going, I could, if I wanted to be an overachiever. But anyways, there you go. Same amplitude, half the wavelength. A baseball bat exerts a force of east on a ball. So I'm going to say this way is east. So it's going to exert a force like that, this way, on the ball. Average force of this is going to be 600 newtons. Imparting an impulse of 3.6 Newton seconds east on the ball. All right, we're going to call those numbers positive. Calculate the amount of time the baseball bat is in contact with the ball. Well, that's pretty easy. Impulse equals this Ft, F delta T. Delta T equals impulse divided by force. 3.6 Newton seconds divided by 600 newtons. Make sure you have two significant figures. This has two significant figures. This one had 3. Two significant figures, 0.60 seconds, not 0.6. That's one significant figure. Make sure that you have 2 for your answer. What is the impulse of the ball on the bat? This is the bat on ball. The impulse of the ball on the bat equals 3.6 Newton seconds that way. Okay, the ball pushes same impulse the other way. Do a thought experiment with a compass. The needle points north. So if I take a compass and put it here, the south side is going to be attracted north, north to south. It will point this way. Therefore, there's a magnetic field that goes like that. Goes like that. Goes like that. The magnetic field. All right, that would be what it looks like. At least 3 magnetic field lines between them. Make sure you can draw magnetic field lines on a bar magnet. Form closed loops. Like that. Of course, it's symmetric. It's actually symmetric in 3 dimensions. We're only drawing it in 2. Make the field lines closer together near the poles. And we'll do our thought experiment again. If I take my compass and put it here, the south side will be attracted that way. So these are coming out of the north side. That's the direction. Make sure you can draw the magnetic field lines around various, a bar magnet and different configurations like that which are in your notes. Determine the magnitude of the acceleration of the car. Well, the definition of acceleration is delta V over delta T. So let's just find some data points. I'll find 2 data points. I'll say 0 meters per 0 seconds and 0 meters per second will be 1. And the next one I will use will be 8 seconds and 10 meters per second. All right, so what do we have? Delta V is going to be 10 meters per second minus 0 meters per second. Delta T is going to be 8 seconds minus 0 seconds. Is going to be the acceleration for number 57. Calculate the total distance the car traveled from 4 to 8 seconds. You can either find the area under the curve, or you can just say the distance traveled is the average velocity times time. The average velocity between 4 seconds and 8 seconds is, average velocity is V initial plus V final divided by 2. It's the numeric average. Let's see, at 4 seconds, it looks like it's 5 meters per second. And at 8 seconds, it looks like it's 10 meters per second divided by 2. So that's 15 divided by 2, which is 7.5 meters per second. So the average velocity is 7.5 meters per second, and it does that for 4 seconds. It's 4 seconds, the time interval between 8 and, so it's going to be 30 meters. The time interval between 4 seconds and 8 seconds is 4. All right, so that is the answer, 30 meters. Parallel circuit, know your circuits. That's a parallel circuit. And, know the idea where if you have two resistors, or whenever you add a resistor in parallel, the equivalent resistance goes down. We have an ammeter. We have R1 and R2. 30 volts. Determine the equivalent resistance of a circuit. All right, well, we know this one's 20 ohms, but we don't know that one. So we can't use our equation. We do have an equation for a parallel, but we don't know R2. So we can't use that. But the whole idea is that we're going to replace this with an equivalent circuit that looks like this. Our equivalent, that doesn't look like equivalent, but it is, trust me. 3.0 volts, 30 volts, and we had 2 amps, is it? Yes, it is, 2 amps. 2 amperes flowing around here. So therefore, we could just solve our equivalent in this circuit. So R equals V over I equals 30 volts divided by 2 amps. All right. Since it's a simple circuit, the voltage across our equivalent is 30 volts, and it's a series circuit, so the current is the same everywhere. So that looks like it's going to be 15 ohms. All right. 15 ohms, well, I can feel good about that. That's less than 20. It has to be. Couldn't be more. If you got more, you had a problem. Calculate R2. All right. Well, I have R equivalent. I have R1. I can calculate R2. 1 over R equivalent minus 1 over R1, just bring R1 over the other side, equals 1 over R2. I want R2, so let's invert both sides. All right. So plugging these numbers in, we have 1 over 15 ohms minus 1 over 20 ohms. And If this was 20, our equivalent would be 10. So it's got to be, it must be more than 20 ohms. Let's see what it is. 60 ohms, yes. 60 ohms is R2. 60 ohms. I can feel good about that answer. A 28-gram rubber stopper is attached to a string and whirled clockwise in a horizontal circle with a radius of 0.80 meters. The diagram in your booklet represents the motion. There it is, right there. The stopper maintains a constant speed of 2.5 meters per second. Okay, constant speed. Of course, the velocity is always changing. Calculate the magnitude of the centripetal acceleration of the stopper. All right. Well, centripetal acceleration, AC equals V squared over R equals 2.5 meters per second squared over the radius, which is 0.80 meters. 7.81 meters per second squared. Let's see how many significant figures I should have. Let's see, 2. Well, actually 2. All right, looks like 2. So 7.8 meters per second squared is the centripetal acceleration. Calculate the magnitude on the diagram. Draw an arrow representing the direction of the centripetal force. Well, it's going around a circle like that. The centripetal force is in the direction of the net force. Something in uniform circular motion there's a net force towards the center. So this is the direction of the net force, which is also called the centripetal force, which in this case would be the tension, force of tension. And of course, at this point, you also need to know that the velocity is this way, although that's not what they asked you here. Velocity is that way, and the speed is constant, and the acceleration is also in this direction. It's also towards the center because the net force is towards the center. Know all those things for uniform circular motion. We're on part C now. This is one of those reading problems. They do this a lot now. I want to make sure you can read. It says, auroras over polar regions of the Earth are caused by collisions between charged particles from the sun and atoms in the Earth's atmosphere. The charged particles give energy to the atoms, exciting them from the lowest available energy level, the ground state, to higher energy levels, excited states. Most atoms return to the ground state within 10 nanoseconds. 10 nanoseconds. All right, so that's 10, and let's look up nano. I believe that's 10 to the minus 9 seconds. Look that up. 10 nanoseconds. Look up those prefixes up there. You have plenty of time. Don't start the bleachers. Yeah, I'm done. I'm done. I'm so fast. Please give me a gold star for being done first. You must be so proud of me. And my parents must also be so proud because I'm done first. And I'm staring at the bleachers. So look it up. Make sure you don't make that mistake. 10 nanoseconds. There we go. Now, if we look at question 66, it says, what is the order of magnitude of the time in seconds that most atoms spend in the excited state? This is a garbage question. We don't know the answer to this, but the state wouldn't give on this one because they didn't say most atoms. They said what is the order of magnitude in time that most atoms spend in the excited state? They said most atoms return to their state within 10 nanoseconds. They didn't say that at 10 nanoseconds. So most of them could have dropped down in 1/10 of a nanosecond. So it's really a garbage question, but we have to deal with it anyway. So here it is. What is the order of magnitude of time in seconds that most atoms spend in the excited state? Well, what is 10 times 10 to the minus 9? Well, we want this to be a 1. We basically want to know what power of 10. But this is multiplied by 10. So let's make this 1.0 times 10 to the... So I've made this one smaller. I have to make this one bigger. Right? So these are the same number. Look, this is the second time we've had to do something like this. Make sure you can do that. So this one is, what order of magnitude is it? -8. That's what they're looking for. What is the order of magnitude, time in seconds that most atoms spend in an excited state? -8 is the order of magnitude. Not 10 to the -8, although they did give on that and they actually gave credit. They initially weren't going to give it. I would think this year it just needs to be -8 is the order of magnitude. So order of magnitude is just the power of 10. All right. Make sure you know that. Calculate the energy of a photon in joules that accounts for the red glow of the aurora. And later it says, in higher regions of Earth's atmosphere where there are fewer collisions, a few of the atoms remain in the excited state for longer times. For example, oxygen atoms remain in an excited state for up to 1 second. These atoms account for the greenish and red glows of the auroras. As the oxygen atoms return to the ground state, they emit green photons of frequency 5.38 times 10 to the 14 hertz, and red photons 4.76 times 10 to the 14 hertz. These emissions last long enough to produce the changing aurora phenomenon. Calculate the energy of the photon in joules for the red glow. All right, so we have the frequency of the red glow. The frequency is 4.76 times 10 to the 14 hertz. And we want to know the energy in joules. Energy of a photon equals Planck's constant times the frequency. Planck's constant is, let's look that up. I don't remember it, 6.63 times 10 to the -34 joule seconds times the frequency, which is 4.76 times 10 to the 14 hertz. All right. We will get joules because this is joule seconds. Hertz is per second. All right. Equation, substitution, units, answers to units. Explain what is meant by an atom in the ground state. The ground state is the lowest. It's when the valence electrons are in the lowest possible energy state, so in the lowest energy orbitals. That's the ground state. A girl rides her bicycle 1.4 kilometers west, 0.7 south, 0.3 east, 12 minutes. The vector diagram in your answer booklet represents, so we have the 1.4 kilometers, 0.7. We're going to have to add the 0.3 kilometers east. Use a scale of 1 centimeter equals 0.2 kilometers. So 1 centimeter on the page equals 0.2 kilometers. In the girls' world, it's a girls' world. Draw a vector representing a 0.3 kilometer east displacement. Label the vector with its magnitude. All right. She's going to go east, which is this way. So I grunged up protractor here. 0.3 kilometers multiplying by ones equals 1.5 centimeters. All right. All right, let's draw 1.5 centimeters. It's a line, that's not a vector. Got to put a direction on it. And its magnitude is, of course, 0.30 kilometers. It doesn't look like a point. There we go. Make sure you're accurate within half a centimeter. Otherwise, they're going to ding you for points. Draw the vector representing the resultant displacement for the girl in the entire trip. She started here and ended there. That's it. She started here, ended there. That's the way she went. And label the vector R. There's our vector R. Calculate the girl's average speed for the entire trip. Her average speed is distance divided by time. Her distance that she traveled was 1.4 kilometers plus 0.70 kilometers plus 0.30 kilometers and divided by 12 minutes. 0.20 kilometers per minute. 0.20 kilometers per minute. Determine the magnitude of the girl's displacement for the entire trip. All right, well, I think that I'm going to take a ruler and measure it. I'm going to use this, I'm going to do this graphically. So I'm going to take the ruler, and that looks like it's right exactly 6 centimeters, actually. So, so she traveled 6 centimeters on the page, but we need to convert that to kilometers. And we want centimeters to go away. So we're going to take 1.0 centimeters. Oh, break the lid. 0.20 kilometers. And what do we have? 1.2 kilometers. Does that make sense? Sure, that makes sense. That's 1.4. 1.2 seems reasonable. 1.2 kilometers. Determine the measure of the angle in degrees. Okay, the measure of the angle. So let's measure 32 degrees. 32 degrees. A light ray of frequency 5.09 times 10 to the 14 hertz. Beautiful. We can use our reference table. So let's get that reference table handy. Gave us the frequency, so we can use, that's a flavor of yellow light. We can use the yellow to do traveling in water. All right, and goes from water to air. At the interface, part of the ray is reflected and part of it is refracted. What is the angle of reflection at the interface? Well, that's the weirdest thing I've ever seen. So I guess we have to draw the normal. You get it? You get the joke? Aim for... All right, so I've drawn my normal. Always draw a normal. Some of you refuse to draw a normal. Don't know why. You just do. You just aren't going to be drawing normals. Oh, well, I tried. What is the angle of reflection of the light ray at the interface? 35 degrees. All right. 35 degrees. On diagram, use a protractor and draw the reflected ray. All right. So 35 degrees. 35, right there. There we go. Reflected off 35 degrees. Let's make sure it's 35. That looks like it's 35 to me. All right. Calculate the angle of refraction as it enters air. All right. Angle of refraction. I'll call this medium 1 and this medium 2. N1, looking up in the reference table, is 1.33. N2 is 1.00. Angle of incidence equals 35 degrees. We want to know what the angle of refraction is. Let's use Snell's law. N1 sine of theta 1 equals N2 sine of theta 2. Let's see what theta 2, put a 2 there. Theta 2 equals N1 sine of theta 1 all over N2, and that's the inverse sine of all this stuff. Yeah, it's terrible. I didn't write that very well at all. Anyways, sine of negative 1 of N1, 1.33. Sine of theta 1, 35 degrees, divided by 1. Let's see what that comes out to be. $49.7 degrees. 49.7 degrees. Let's see, does that make sense? It's going to speed up, so it needs to be fast. All right, yeah, 49.7. We probably have to draw that. Let's see what it says. Calculate the angle of refraction as it enters the air. Identify at least one characteristic of the light ray that is the same in both the water and the air. Same characteristic, the frequency. The frequency is the same in the water and air. That's the only thing that is the same, I think. The wavelength is going to change, the speed's going to change. I'm actually going to draw that, 49 point, like that. Something like that. Bends away from the normal because it speeds up. Determine the total work done by the 30.4 Newton force. All right, work equals force times displacement, where the force and the displacement have to be in the same direction. The force is this way, the displacement is that way. They're in the same direction, so the force is 30.4 newtons. The displacement is 6 meters. All right, that's the work that this force did. We're going to want 3 significant figures because that's what everything has. Calculate the total increase in gravitational potential energy. So you did work that increases the energy of the system. Part of the increase in the energy is going to be gravitational potential energy. Part of it could be internal energy if there's friction, and part of it is kinetic energy if it's still moving. When we get there, state what happens to the kinetic energy as it goes along. Let's see. Kinetic energy, of course, is 1/2 mv squared. Well, the mass stays the same. What happens to the speed? If the speed increases, the kinetic energy is going up. If the speed remains the same, kinetic energy is the same. If the speed lowers, it's getting less. Let's see. A force is used to slide a 4 Newton distance in meters at constant speed. It's constant speed, so kinetic energy remains the same. 84. Kinetic energy remains the same. They said the speed remains the same, therefore the kinetic energy remains the same. State what happens to the internal energy. Well, as it slides along the incline. I skipped a problem. Calculate the total increase in gravitational potential energy. All right, so we'll say potential energy here is 0. What's the potential energy here? Potential energy is mgh. So mg delta h, it's a change in potential energy. Mg is 40 newtons. Recognize that. That's the weight. Mg is the weight. Don't treat it like a mass and multiply by g. It doesn't make any sense. Shows you don't know what you're talking about. H, 3 meters, equals 120 joules. All right, so we got it up here. 120 joules of potential energy. We did 182 newtons. Wow, newtons. That's joules. That's joules, not newtons. Joules. 182 joules of work to get it up there. So some of that, 62 joules, must have been internal energy. And that says 85. So this was 82, I guess. 82. The potential energy is 120 joules. What happens to the internal energy of the crate as it slides along? Internal energy increases. 85. Q increases. Remember, internal energy is Q. Q increases as you go up, and indeed, when it gets to the top, 62 joules of internal energy has heated up. Anyways, the ramp heats up, and so does the crate. It doesn't really heat up, it increases its thermal energy. All right, that's the end of the exam. I hope you did well. I hope you kept track. Hope you tried it. Maybe check the answers and keep track, see how many you're getting right. Later.